All right, let's dive right in. Today we're unpacking an epic, centuries-old philosophical battle. But this isn't just some abstract ivory tower debate. This is the invisible math literally running your life. In this explainer, we're going to explore this profound tension in mathematical modeling between eternal constancy and chaotic evolution. It's a fundamental clash between order and chaos, and it dictates how we predict everything, from tomorrow's weather to your 401k, right down to the entire global economy. So here's the ultimate mathematical dilemma. How exactly do we model a world that absolutely refuses to sit still? I mean, think about it. This is the daily, grinding reality for researchers and mathematicians. They have to use math, which is at its core a timeless, perfectly unchanging language, to describe a reality that is completely bound by time and constantly mutating. It's kind of like trying to paint a portrait of someone who's literally sprinting around the room, and on top of that, their facial features keep changing while they run. To ground us here, the brilliant statistician George Box famously said, "All models are wrong, but some are useful." And honestly, that perfectly sets the pragmatic tone for our explainer today. Because reality is just so incredibly messy, modelers are constantly forced to balance rigid, perfect equations with chaotic, real-world data. A model is never going to be a perfect mirror of reality, right? It's just an approximation. The real magic and the real challenge is deciding exactly how it should approximate that reality. Now, we can view this entire conflict through the lens of classical philosophy. Think of it like a heavyweight boxing match. In one corner, we have the Platonic ideal. This is the pursuit of constancy, eternal truths, and invariance, the comforting idea that underneath all the noise of the universe, there are fixed, unbreakable rules. And in the opposing corner, we have the Heraclitean flux. This is the reality of pure chaos, perpetual divergence and mutation. It's that old saying that you can never step in the same river twice, because the fundamental rules of the game are quite literally always shifting. Okay, let's start by looking closely at the first camp, the Platonic ideal, which we can call the perspective of constancy. When modelers operate from this perspective, they are hunting for the underlying mechanics of a system that remain fundamentally unchanged over time. They are looking for systems where you can look at the data and confidently say, yep, it is exactly the same as it ever was. They want predictability. They want certainty. Frankly, it's the mathematical equivalent of wrapping yourself in a warm blanket. So, how is this constancy actually written mathematically? Well, in calculus, the rate of change over time is expressed as dx over dt. When a system reaches a state of perfect constancy, dx over dt equals exactly zero. Zero change. None. The system has effectively flatlined into a state of perfect, completely predictable order. We call this mathematical comfort zone a steady state. It's an equilibrium point where observable conditions just cease to evolve. A really great example of this is found in Markov chains. Think of it kind of like a perfectly shuffled deck of cards. Eventually, the randomness just settles into a predictable long-term pattern. Certain systems converge to what's called a stationary distribution. And the beautiful part is, it doesn't matter where the system started. The long-term probabilities just lock into place and stay strictly constant. It is safe, predictable, and exact. To visualize this, picture an attractor as basically a giant mathematical magnet. Even if a system starts off a little chaotic or noisy, if there's a steady state attractor present, the system naturally gets pulled right toward it. It'll eventually just relax into this nice, predictable equilibrium. The math essentially guarantees that order will ultimately prevail over whatever initial noise was there. And this search for constancy isn't just theoretical play. It gives us some of our most powerful, bedrock scientific laws. We rely heavily on invariance. These are immutable rules, like the conservation of mass, energy, and momentum. Mathematicians use things like Noether's theorem, which beautifully links deep, underlying physical symmetries directly to these unchanging laws. We even have the wild Poincaré recurrence theorem, which actually dictates that, in certain bounded systems, history is mathematically doomed to repeat itself, eventually returning to a state arbitrarily close to exactly where it started. But here is where we have to pivot, and pivot sharply. Let's step into the antithesis, the Heraclitean flux. What actually happens when the world absolutely refuses to sit still? What happens when those fundamental rules of the game constantly mutate? Well, if the perspective of constancy is the true, pure mathematical ideal, the perspective of flux argues that out there in the messy real world, that pure constancy is actually a total illusion, a false perspective. Enter chaos theory. Chaos theory introduces something radically different, the strange attractor. Instead of a system settling down to a single point, a strange attractor maps an infinite non-intersecting path. The system stays within a certain defined boundary, sure, but it never ever crosses its own path. This is absolutely fascinating because it means the system state is fundamentally novel at every sequential step. It never perfectly repeats. It's perpetual novelty, even if the underlying rules driving it are completely deterministic. Which brings us right to the heart of chaos theory, famously known to all of us as the butterfly effect. In nonlinear dynamical systems, there is an extreme, massive sensitivity to initial conditions. This means if you have arbitrarily small perturbations, let's say measuring a temperature at 71.0001 degrees instead of exactly 71 degrees, those tiny microscopic differences will snowball into exponentially diverging trajectories over time. Because of this, long-term prediction goes out the window. It becomes entirely impossible, which is exactly why we can't reliably tell you if it's going to rain 3 weeks from next Tuesday. And listen, this chaos isn't just some mathematical thought experiment. It is practically embedded in all the data we collect. A stationary process assumes that historical data will reliably predict the future, but reality is dominated by non-stationarity. In fields like finance, ecology, or epidemiology, the parameters literally drift over time. Exogenous shocks happen, like, say, a sudden global pandemic that entirely shatters existing financial models overnight. The actual relationships between the variables themselves mutate. A math model trained purely on yesterday's data will often totally fail, because today's environment simply isn't the same as it ever was. Let's ground this philosophy in a highly concrete example. Think about fluid dynamics versus climate change models. If you're an engineer modeling water flowing through a pipe, you rely on the Navier-Stokes equations, the fundamental math of fluid flow. You get to assume immutable rules, the conservation of mass, perfect constancy. But if you're modeling climate change, you have no such luxury. You cannot rely on steady-state assumptions because historical baselines simply don't represent current or future planetary conditions anymore. You are forced into the deep end, modeling transient dynamics, shifting parameters, and pure non-stationarity.
So, the big question is, how on earth do we survive this tension? Well, the modern mathematician has to achieve a pragmatic, modeler's synthesis just to keep their head above water. Their task is incredibly tough. They have to carefully extract the unchanging, stationary components from a reality that is constantly in motion. They have to acknowledge and respect both the timeless mathematical rules and the incredibly messy, temporally bound, evolving phenomena they're trying to study.
To actually pull this off, modeling has had to evolve from using rigid, static equations into an iterative, highly adaptive loop. Here's how it works today. First, you deploy your initial deterministic framework. Second, you continuously ingest chaotic, fresh, real-world data. And third, you dynamically recalibrate your rules and parameters based on that data. You are essentially letting the math evolve right alongside the changing world.
We can think of these adaptive methodologies as the Bayesian bridge. They act as highly practical concessions to the chaotic flux of reality. Techniques like Bayesian updating, data assimilation, and rolling window regressions allow a mathematical model to literally learn. It's the math of changing your mind when you're presented with new evidence. Instead of assuming perfect, unchanging constancy, Bayesian updating takes the new evidence and updates the probability of a hypothesis. It brilliantly holds both the Platonic ideal of underlying rules and the Heraclitean flux of new data in this perfect, productive tension.
But I need to leave you with a serious warning here. If a modeler forgets this delicate balance, if they get seduced by the sheer elegance of the math and over-rely on constancy, the results can be absolutely disastrous. It leads to catastrophic overfitting to historical data. In macroeconomic forecasting or algorithmic trading, failing to anticipate non-stationary structural breaks, which are often called regime shifts, means your model won't just be wrong, it will completely blindside you the second the real world decides to change its rules. Which brings us to our final, lingering thought. As computational power explodes and our systems become insanely complex, we really have to ask ourselves, will the highly complex AI-driven mathematical models of the future uncover even deeper constants currently hidden beneath all this noise? Or will they be forced to abandon the Platonic ideal altogether and just fully embrace pure, unadulterated chaos? It's a profound tension, and honestly, how we answer it is going to shape the entire future of human knowledge. Thank you so much for joining me on this explainer today. And remember to always keep questioning the constants in your own world.